Let's settle with the duel in Clash Royale. I'm coming after you. Let's settle with the duel. I'm coming after you. I'm coming, settle with the duel.
To figure out if something is an acid, a base, or neutral, we can use an indicator. We put 15 drops of our substance, hydrochloric acid, in a test tube, and all we need is a few drops of universal indicator solution, and we look to see what color the solution turns. Here the solution turns bright red, so we can compare that to our chart and see that red corresponds to a pH of 4 or lower. That means we need to do further testing. It could be a 2 or a 1 or a 3. When testing it a second time, using universal indicator solution for pHs 1 to 7, we can see it's a bright red color. According to our second chart, that corresponds to a pH of 1. Now we can test sodium hydroxide. With 1 drop of universal indicator solution for pH 4 to 10, it turns purple. According to our chart, purple means pH of 10 or higher. If we test calcium hydroxide, we also get a purple in color, which again will correspond to a pH of 10 or higher. We would need further testing, however we won't do it at this time. While testing citric acid, we can see that universal indicator solution pH 4 to 10 turns red color. That corresponds on our chart to a pH of 4 or lower. So we need to do further testing to figure out if it's a 4, 3, a 2, or a 1. By using universal indicator solution for pH 1 to 7, we can see that the citric acid turns orange. And on our chart, orange corresponds to a pH of 2.
lot of stuff. You're welcome. All right.
We will see what happens when metal oxides react with an acid. We need test tube, copper oxide, and dilute hydrochloric acid. Take some copper oxide in the test tube. Add dilute hydrochloric acid to it, drop by drop, and shake. You will see the solution has turned green. The copper, which was in insoluble form in copper oxide, has reacted with hydrochloric acid and formed a soluble salt with the chloride ion from the acid and formed copper chloride. The solution now contains copper chloride. When metal oxides react with an acid, metal oxides form a salt with the negative ion of the acid. In this case, the reaction can be depicted as CuO plus 2HCl gives CuCl2 plus H2O.
If we connect an electrolyzer filled with distilled water to a source of direct current, we can observe a slow evolution of gases. After some time, we notice that the volume of the gas released at the cathode is double that of the gas formed at the anode. To identify the gaseous products of the reaction, we collect each gas in a test tube and check its behavior in the presence of a glowing splint. The characteristic cracking sound proves that the gas released at the cathode is hydrogen. The ignition of the glowing splint is evidence that the gas collected from the anode is oxygen, which supports combustion.
When water dissociates, it breaks apart into an equal number of hydrogen ions and hydroxide ions. In contrast, when other substances dissociate, they may release more hydrogen ions or more hydroxide ions. For example, hydrochloric acid releases more hydrogen ions as it dissociates, and sodium hydroxide releases more hydroxide ions. Depending on its concentration of hydrogen ions versus hydroxide ions, a substance can be classified as either an acid or a base. The pH scale measures how acidic or how basic a substance is. It ranges from 0 to 14, with 7 being neutral. When a substance has a pH of 7, like water does, it releases an equal concentration of hydrogen and hydroxide ions. When a substance has a pH of greater than 7, it's classified as a base and releases a greater concentration of hydroxide ions. The more hydroxide ions that are released, the the more basic of the substances. Bases tend to feel slippery and are often used as household cleaners. Milk of magnesia and ammonia are both common bases. When a substance has a pH of less than 7, it's classified as an acid and releases a greater concentration of hydrogen ions. The more hydrogen ions are released, the more acidic the substance. Acids tend to taste sour. Lemon juice, stomach acid, and coffee are all examples of acids.
I'm going to show you an electrolysis of water setup. So we have a mini Hoffman apparatus, and I'm going to take this little test tube here, and I'm going to dip it under and fill it completely with a 3 molar sodium hydroxide solution. I'm going to do the same with this one. So since we're starting with that completely filled up with solution all the way to the top here, it's going to allow us to collect gases in each of those. So we're going to run a red lead to the negative terminal of the battery, a black lead to the positive terminal. And when we do that, you can see bubbles starting to originate in there. I'm going to zoom in so we can see that up close. And that gas is collecting on the left and on the right. Over there. So we're going to let that run until we've collected enough to make a measurement. So let's go ahead and make a measurement here. So we're going to start by unclipping this. That way our reaction will slow down and stop. We'll let some of those bubbles collect. So we're going to tip this over. Now you're in a little bit of a parallax there, so this is currently reading about 3.7, 3.8 milliliters for the smaller of the two. And the larger of the two is currently at about 7.6, maybe 7.7. Okay, so 3.8, 7.6, looks like we have twice as much gas on the one side than the other. Let's hook these back up. So we can fill them up a little bit more. So now we need to test what those gases are. So to do that, we're going to do a simple splint test. Let me zoom out a little bit. So our test tube on our left here, the one that's filled up with more, we're going to test that first. We're going to let the other one go for a little bit while we do that test. So to test that, what we're going to do is we're just going to pick it up and we're going to insert a flaming splint into it, see what it is. So this is the one that has more gas present, looks like about twice as much gas. So we're going to let the solution pop out of there. Okay. And so from that noise, we know that we have hydrogen gas present. So now we want to do a test on the other one to see what gas is present over there. And keep in mind that we're only testing about a half-filled container here, so we're up to about 4.5 milliliters of this other gas. What we're going to do here is we're going to test to see what this is. The splint is ready. We're going to put that flaming splint into there. And we can see that that lit back up, which is indicative that we have oxygen gas present. So what we ended up with was 3.8 milliliters of oxygen gas and 7.6 milliliters of hydrogen gas. Because those last couple didn't work out quite so well, I'm going to run this one more time with the flame test. So this has now been filled all the way. And we're going to take this one. This one is the one that is completely filled up. And there's our successful hydrogen test. Okay. And the other one was not able to fill up all the way because the other one, when the test tube here is filled with hydrogen gas, the electrolyte is no longer in contact with the electrode. So we are now just passing 5 milliliters of gas, actually just past 6. So we're going to do a second test with that. We're going to do the oxygen test. So we're going to grab this, put it upside down, and you can see that it easily ignites back into on fire, confirming the presence of oxygen. So we have our flint out, and we have our flint back on fire. So again, we're seeing a 2-to-1 ratio of hydrogen gas to oxygen gas, and confirmation of what the two gases are.